All right. So here's the thing. I have chocolates. So this is kind of my desperate measure to get people to talk. So today, those of you that are going to answer questions will get +2. But those of you that are going to ask a question will get a chocolate. So here we go. And I'll be throwing it. So no falling asleep. Stay with me and have a chocolate after your lunch. So here it is. Either you eat it or I will eat this whole thing, which is not good for my diet. So how else can I encourage you guys to talk? Other desperate measure would be quarters later on in the semester. I'll be sending quarters down. So let's see how desperate I'm going to get. All right, so take a minute, look at these, and I want everybody to talk to me today. Okay, I'm going to be quiet for a minute. Look at the recap questions. I don't think so because we're still... Yeah, we're still in basic chromatography, which week 3. I'll put up, Gary is going to start GC on Friday, so I'll put up his lecture notes soon and open it up. Okay, name examples of adsorptive chromatography. Grace. Yes, hydrophobic interaction chromatography, they are adsorbing to the column via hydrophobic interactions. What else? Other than hydrophobic interactions, what else can be? Affinity chromatography is one. Yes, Lauren? Ion exchange, whether it's cation or anion, they are adsorbing via electrostatic interactions on your stationary phase. Good. Is there anything else? I think we got it all. What molecular interactions between solute and stationary phase are involved? Forget about size exclusion for a minute. We didn't cover that. Ion exchange, I think I just said it. What interactions? Axel? Electrostatic. HIC? Hydrophobic. Affinity? A cocktail of them. Hydrogen bonding, hydrophobic, ionic, or electrostatic, van der Waals, any form of non-covalent interactions can occur when in affinity chromatography. What is the difference between cation and anion exchange chromatography? Go ahead.
So for anion exchange, the column is positively charged, and for cation, it's negatively charged.
In anion exchange, the column is positively charged and is exchanging negatively charged ions between the column or the stationary phase and the mobile phase. And the opposite is true for cation. What do you increase, or how do you increase the strength of the mobile phase in reverse phase chromatography? Increasing the strength of the mobile phase in reverse phase chromatography. First, you have to remember in reverse phase chromatography what would be your stationary phase and what would be your mobile phase. Jordan, yes. No, you're Devin.
Oh, Devin.
Yeah, not Jordan. Devin. Okay, sorry. Who's Jordan? We don't have a Jordan even in this class. Okay, Devin, go ahead.
Mobile phase is polar, so you want to make it more polar.
Okay, so the mobile phase is polar, so you want to make it more what?
More polar.
It's already polar. and your stationary phase is nonpolar. You want it to compete with the stationary phase for the compound, so you make it less polar. So you make it similar to the stationary phase. What about in hydrophobic interaction chromatography? How would I increase the strength of my mobile phase? Remember, increasing the strength is making it stronger for the solute to interact with it, rather than interacting with the column. In HIC, remember that we precipitate the protein on the column by high salt concentration. Now, we want to remove them from the column. What do I do to the mobile phase? Started with high salt concentration, protein precipitated on the column. Now I want them to come out. What do I do with my mobile phase? I decrease the concentration of the salt. I make the mobile phase stronger that way. In ion exchange, I can change two things. What can I change? It doesn't matter which direction of one of them. I want to change basically you want to change the charge on your solute. If it's positive, you want to make it lose its positive charge. Or you want the stationary phase, its charge of the stationary phase to be covered. So what would you do? Alex? You can change the pH in either direction depending on whether it's anion or cation. What else can you do? You can add something to your mobile phase. Add salt. So the salt will block charged groups on your stationary phase, then it will change the selectivity. It will prevent your solutes from interacting with your stationary phase. In affinity chromatography, how do we increase the strength? There are two ways. There's a non-specific way and there's a specific way. Okay, you have a quiz next Wednesday. You really need to start studying so you do well on the quiz. Okay. Nobody will remember this.
You can change the pH or the salt of the solution, or you can, that's the non-specific, or the specific is add the ligand or whatever attaches.
Excellent. So you change the pH or the salt. That means you're changing the selectivity of the stationary phase to your compound. So they're no longer interacting via very specific interaction. You change the conditions. You change the ionic status of them. That's non-specific. Specific, whatever ligand you have on the column, on the stationary phase, that is interacting with the molecule, you can add the same ligand in your mobile phase. So now the mobile phase has a compound that will interact with your solute. So that will compete with the column. What is the order of elution in HIC? Meaning most hydrophobic will leave first or least hydrophobic will leave first in hydrophobic interaction chromatography. Come on, this is common sense. The least hydrophobic will leave first because the more hydrophobic your compound is, the more it's going to interact with the column. In ion exchange, the most charged or the least charged will leave first. Common sense? Least charged. In size-exclusion, we haven't talked about that. But when you study, please use this as your guide. Do you really know all of this? A lot of these questions are basically going to be part of your quiz or test. So use these as kind of your study guide, plus the sample quizzes from the past. Okay. Remember, asking a question will give you a chocolate. Do you have any question you'd like to ask now? Who's going to receive the first chocolate? Apparently me. So stays here. Okay. Size-exclusion chromatography. So size-exclusion chromatography have multiple names and they all mean the same thing. So if you hear gel permeation, it means size-exclusion. if you hear size exchange, it means the same thing. So it's just people use different terms, but it really means the same thing. Or molecular exchange chromatography, that means it's exchanging based on molecular size. Okay, so here in this chromatography, there is no chemical interaction. It's basically physical based on size. So the molecules separate based on how big they are. So as it's illustrated here, your packing material has pores. Okay, so maybe if I draw it, can illustrate it a little better. So you pack your column with a slurry of your stationary phase, which in this case are particles that are inert, will not interact with your molecules. And then, so you're packing them, so you have really tight particles packed together. But these particles have pores, different size pores. So that means they're porous. So your solute, if it's small, it will go through the pores. So when you inject your sample, it's going down, and then you have your mobile phase going down. So your mobile phase is actually, going around, inside, everywhere. And then your solute is traveling with the mobile phase now, but it can be delayed because it can go through the pores and be delayed if it's small. If it's large, it will not possibly go through. So the large molecules might not go through the pores, so they will travel faster with the mobile phase. They will not be delayed by going through the pores of your stationary phase particles. So the largest particles that can not fit in any of the pores travel with your mobile phase, and we call that they travel with the void volume. That means the volume of the mobile phase that constitute the outside of the particles. Okay, so that's another illustration. So your bigger molecules travel with the mobile phase and doesn't go through any pores, whereas the smaller ones goes in and out, and get slowed down. So in this chromatography, there are different types of volumes that we refer to. So the void volume is the volume, like I said, between the particles, the volume that goes through between the particles of your stationary phase and leave the column. So that the largest molecule leaves with the void volume. Okay, larger than the pore side, but not every time you inject a sample you might have large particles like that, but sometimes you do. Okay, so that's the void volume. The internal pore volume, that's the volume of the mobile phase that goes through all the pores. We call that internal pore volume. The total permeation volume, hence gel permeation name, of size-exclusion, that means the same thing, is the volume of void volume plus internal pore volume. So that's the total volume. One other volume that is important is the volume E, or elution volume. That's, let's say this is your compound of interest. It took volume E to get it out, certain amount of milliliter to come out. Any question? I will. It does count. So the VE volume is the volume of the mobile phase that took your solute to come out. So how many milliliters that took that solute to come out? If it's in the middle, that's a medium-sized particle, so it's not small. It didn't take the entire volume to come out. and it's not too large, so it's not the void volume. So it is the volume that is in between that took one particular compound to come out. One particular compound of a particular molecular size. So we use size exclusion chromatography often to not only separate, but to kind of estimate the molecular weight. In order to estimate the molecular weight, what we can do is we can actually run standards. We can run standards molecules of different molecular size and plot the log molecular weight of the different standards against a partition coefficient, which we call it available partition coefficient, KAV. So what KAV is the ratio of your elution volume of that particular compound that you want to determine the size of minus the void volume over the total volume minus the void volume. If the particle is too small, like vitamin B12, for example, that means your VE is almost as big as VT, total volume. It means that it took almost the entire volume, elution volume, was the entire volume of the column to elute. That means it's the smallest. So this would be, the ratio would be 1. When VE nears VT, then your KAV nears 1, that means it's the smallest. And the opposite is true. When VE is too small, that means it's almost close to the VO, void volume, then this number becomes too small, the denominator becomes too small, then KAV becomes too small, and that's indicative of a large molecular weight. Okay. Clear? Hope. So, in size exclusion chromatography, what kind of interactions do we have with our stationary phase? Everyone in the class? None. Unanimously. Okay, good. None. Inert. No interaction. Purely on size. Okay, this is your friend table in chromatography. This is where you need to study a summary of all of your separate, and it's also a table 12.3 if you have your book. It's bigger, it's easier to read from. So the person that wrote the chapter did a good job here. I wrote the chapters. Okay, so anyway, separation mode. What would be your stationary phase? What would be the mobile phase? This is typical question. I will give you an example of molecules, and I tell you what would be your mode of separation. What would be your stationary phase, mobile phase? How do you increase the strength of that mobile phase? Which compound will elute first and elute last? What type of interaction? Typical question. Okay, so learn it. It's a summary of everything we talked about. There's a question.
I doubt this counts. I'm just wondering, like, if you have any recommendations for how to study this and get all this information down. Like, in the past, if people use like flashcards or just like listening.
Okay, I like throwing chocolate. Okay, so, well, it really depends. Everybody has different kind of style. I do have the recorded lectures, so it would be good to kind of break it down into each concept, and then you can go to where I talk about it, pause, review it, read about it in the book. The book is more detailed than the lectures, but it might clarify something that we went over a little bit fast. But some people like take that table and start to study it, and I do have examples from previous exams and quizzes, and they're on Canvas. So please review those. The key is there, but don't look at the key. Try to solve them as if you're taking a quiz. That will be helpful. Yes?
So majority of this quiz is going to be solely on the basic principles of chromatography.
The quiz is for everything we've covered from the beginning of class. So the first 5 chapters that we talked about, and the buffers and reagents and all the wonderful calculations. that you truly love with all your heart, that would be part of the quiz. And chromatography up to wherever we get to on Monday, because the quiz is on Wednesday. Here you go. There, oh, I can't reach that far, but what?
And then for the exam, are you allowed to use a graphic calculator or can you just use a regular calculator?
What kind of calculator?
A graphic calculator?
I don't,
Or does it matter what type of calculator?
it doesn't matter. I never use the graphing. My daughter uses a graphing calculator. I don't know if there's anything that will.
The reason why some classes put them graphic calculators is some of them are too advanced and you
Don't put notes on them. I don't care. I'll trust you. Whatever calculator you want. Oh, jeez. Okay. We're moving into a very exciting piece, at least for me, is figuring out separation and choosing a method of separation. So the ultimate goal of chromatography is to separate compounds, right? When we say separate compounds, it also means resolution of these compounds or resolution of the peaks. How well we can separate them from each other. The better we separate them, the better we're able to identify them and quantitate them. So if you're working in a lab and I told you, okay, we're going to determine antioxidant content. I'm always going to have this example to bug Ali here. Okay, so you have carotenoids you want to quantitate. What would you do first thing? You know nothing about it. You don't have a method. What would be the first thing that you would do? Common sense. You came to my office and you didn't find me. What's the next thing you would do? Gary's not in his office either. Okay, Kim.
I guess I would look up to see what other people have done.
Yes, you would look up to see what other people have done. I bet you anything you want to do is published already. It's very hard to find something novel these days because it's been years and years and years of research. So the first thing you would do is you go look up what's information is out there about a method, what do we know about the sample, how many different carotenoids I might have in my sample that I need to resolve, what degree of resolution, do I really need them to be very separated from each other, or it doesn't matter, they can be partially separated but I can still identify which is which. If I'm just looking for their presence, it's okay. If I want to quantitate, no, it's not okay because usually I want to get the area under the curve. If I don't have good separation, I can't get quantification. So sometimes you go look into literature and you find, boy, there are like 3-4 different modes of separation that can be used. So here's an illustration, figure 1210. So for some ionic compounds, we will learn this in carbohydrates. The same sugars can be separated by reverse phase ion pair chromatography. We'll talk about that in HPLC lecture, and ion exchange chromatography. So which reference would you follow? Which method would you follow? The same compound, you can use different methods of separation. What would you do? Yeah. Yes. What do you have in the lab? What's available? What column do you have? What expertise you have in? You can start there. If you don't get good separation, you go, okay, this is not getting me the separation I want. I will go to more specific method of separation. I will go to the second reference I found and ask my PI to pay a little bit more money and get the column I need. So you have to do some investigation basically to see first what's out there published, what do you have available in the lab, what do you know about your solutes, how much separation you need to get, and work your way through. Then you know, even in, let's say you chose reverse phase chromatography, even in reverse phase chromatography, there is a C8 column, C18 column, C30 column, C40 column. You go, oh my gosh, now what do I need? Which one do I need, C18 or C40? By the way, which would be more hydrophobic, the C18 or the C40? C40 will be more hydrophobic because it has the largest hydrocarbon. The largest hydrocarbon is more hydrophobic. So you go, okay, what type of compounds? Are they carotenoids or are they isoflavones? If they are isoflavones, they are partially hydrophobic. They're not completely polar or nonpolar. They're somewhere in between. Okay, I will use C18 column. That's enough. Carotenoids, they're more hydrophobic. I need a C30 column or a C40 column. So what I know about the compound helps me select stationary phase, and mobile phase follows. So again, I'm just introducing the principle, but later on in the semester, we're going to get examples on different stationary phase, mobile phase for different compounds that we're going to analyze. And then you go, okay, I'm developing this method. I ran whatever is published in this paper. I followed the exact same mobile phase constitution. It didn't work. It will never work. Taking something that is published and getting the exact same results. Why? Because you have a different column age. You have a different tubing on your HPLC. You have a different detector. You have an older unit versus a newer unit. You will never get the exact same resolution as a published work. So you're going to start thinking, what can I do to get resolution or separation? I might have to consider the elution mode. So you might have started with isocratic. It took 2 hours to finish because you have, let's say, a very polar and a very non-polar in the reversed phase. That one came very quickly and the other one took 2 hours to come out. Can't afford that. So I start working with my gradient, increasing the strength of the mobile phase. Flow rate. Sometimes the flow rate, you can play around with the flow rate to shorten your analysis time and to reduce the width of your peak. If you reduce the width of the peak, you get better resolution, because then you reach equilibrium faster. We'll talk about flow rate a little bit more later. Temperature. When you increase temperature, what do you think happens to the movement of the solute between your stationary phase and the mobile phase? What happens to it? Does it go fast? Speeds up. So the velocity speeds up. And what do you think happens to the viscosity of your mobile phase? Does it go up or go down? It goes down. So viscosity goes down. It helps the solute to move fast. And the solute itself, kinetics would make it move faster. Then you will have faster equilibrium, sharper peaks, and better separation. So in chromatography, we play around with your mobile phase composition, flow rate, and temperature to enhance separation between two peaks. Next week in lab, we'll talk about that when you do the caffeine lab, and I'll show you examples of what we can do. Okay, so some terminology that you need to learn to help us move forward with explaining resolution or separation of two peaks. You will hear retention volume. From the name, the retention volume, what does it mean? Retention, what is retaining on the column? What is sticking to your column or stationary phase? Your solute. So the retention volume is the volume it takes, the mobile phase volume it took to get your solute out. That would be how long the solute stayed on the column from beginning to end, from the beginning of the column to the end of the column. How long did it stay until it came out and was detected by your detector? But the most common term that we use is retention time. Usually the volume varies a little bit based on your flow rate. But the retention time is basically easier to work with, is the time it took for the solute to leave the column from the beginning, from the injection time to the detection time. In order to identify, often we compare the volume, retention volume or retention time to a standard. So in order to identify, and that's what you're going to do for the caffeine lab and also for the GC lab, is you're going to inject a standard and determine where that standard, what time that standard comes out, and then you try to find that compound in your sample based on the retention time. If you have two compounds that were supposed to be separate, 1 and 2, but came as one peak, that means you were not able to see two, you just saw one peak, then you have to do further separation to separate them. You can either change the gradient of your mobile phase, you can change the flow rate or temperature, or you have to go with a different type of chromatography altogether to separate them. Adjusted retention time is basically, there is this peak which we'll talk about it a lot next week in lab, whether it's caffeine or fatty acid lab. You have something we call the solvent front peak. So this is when you inject a sample, from the time of injection, the mobile phase is going through your column as well. At the time the mobile phase reaches the detector is going to recognize something, that something hit that detector. So it's going to recognize that something reached me, although it's not the sample, it's the solvent that reached the detector. You're going to see a blip. That blip could be really high. In chromatography GC, you're going to see a really large peak. And in HPLC, you're going to see a very small peak. It really depends on the selectivity or sensitivity of your detector towards the solvent, sensitivity of the detector towards the solvent. So we call this solvent front, and also it is your void volume that we talked about, the volume that goes through the column between the particles. So that's solvent front. And the solvent front is different between different instruments because you have different lengths of tubings. You see in the lab that there are tubings that connect every unit in the HPLC and every unit in the GC. So if it's longer or shorter, that solvent front will be coming sooner or later. So if we take that into account, we get the adjusted retention time by subtracting the time until you get the solvent front. So by doing that, it's called adjusted retention time. That gives you a little bit better comparison between two instruments, for example, running the same thing. Identification of the peaks is really dependent on the separation factor, the alpha, which is basically the ratio of the adjusted retention time of peak 2 to adjusted retention time of peak 1. So the larger the alpha, the better is the separation. So the longer this time is, the adjusted retention time of peak 2 compared to peak 1, the better is the separation. When this peak starts moving left, this value becomes closer to T retention time for the first peak. When retention time for the second peak becomes closer to the retention time to the first peak, then the alpha goes smaller, and when alpha is 1, you have no separation. Oh, yes.
So what exactly do the peaks signify? Is that like the volume emitting from the column?
What the peak signifies? That's a wonderful question. You get 2 chocolates. That's an awesome question here. I love that part. Okay, what does the peak signify? I'm going to draw it. Actually, I was going to get into that a minute later, but here we go. So that's your column. You have your stationary phase. You're going to inject your sample. So your sample starts off at a very thin layer on top of your column. And then you have your mobile phase that's going to go through mobile phase here. And then the sample starts moving in 2 ways, either in and out between the stationary phase and the mobile phase, and by diffusion as well, from highly concentrated to low, from high concentration to low concentration. So your sample or your molecule or compound, solute, whatever it is, it starts spreading within the column. So it goes from thin, and as it moves, start interacting with the column, start diffusing down and going in and out, it starts to grow bigger. You don't want it to get too wide. If it diffuses too much, if this becomes really wide diffusion, that means you have a problem with your resolution of and efficiency of the column. You don't want it to spread too much. You want it to go in and out and equilibrate between your stationary phase and the mobile phase. The peak is this. So here, as this comes out from here, actually, let me draw it down there. Just maybe a little bit higher so those in the back can see. Let's say the column ends here. Your sample is now diffused this much within the column, and now it starts to come out. It's coming out. So when it comes out, so there's nothing here, and then it starts coming out. Low concentration, and then more of it come out, and then more of it, the highest concentration, and then go back to the lowest concentration, and then all of it leaves the column. That's your peak. And how you detect it is whether it's absorption, refractive index, or conductivity in GC, whatever it is, that would be the time, and that's the peak. The more it's diffusing, if it's like this big, then your peak is really wide. That's a bad peak. The sharper the peak, the narrower is the diffusion, the better is the separation, because if you have 2 compounds and they overlap like that, each one of them is spreading on top of each other, then you're going to get something like this. Because they're overlapping, they're diffusing together. The sharper the sample diffusion is less, it's sharp, then you have really good, nice peak and very good resolution. Of course, there's going to be diffusion, but you do not want a lot of diffusion within the column. You want the movement to be in and out from your stationary phase to the mobile phase and get equilibrium that way, and move in a sharp, tight band. Moving in a sharp, tight band will illustrate a sharp, tight peak. Is that good, Riley? Okay. Well, that's a good question because it will help understand the following. Okay.
Is the peak always like a measure of concentration, or can it vary based on
That's another wonderful question. 2, because I'm not getting a lot and I need to get rid of this bag. Okay, so the question was, and I don't know if you heard that question, but I'm repeating because I'm recording. It's an important question. Does the size of the peak always designate concentration? If it's the same compound, yes. This, if it's the same compound, yes. If we have, like you'll see, you're measuring caffeine. In one sample you have coffee or you have Pepsi. In Pepsi you have less caffeine than coffee, so you'll see smaller peak of caffeine. But in the fatty acid lab, you're going to look at peaks of, let's say, oleic acid and linoleic acid, and you're going to compare which one is greater. This is only qualitative because every compound has a different response factor from detector. So every compound will give you, if it's an absorption, every compound will have a unique absorption. Some compounds will absorb a lot at a particular wavelength, for example, so it gives you a really large peak. But in terms of concentration, it won't be bigger than another compound that absorbs little at that particular wavelength. The only way to accurately quantitate is to actually have a standard from each compound. Okay? That's a wonderful question. Okay. Any other wonderful questions? See, it's good. It's better than me just talking at you. All right. So we want to determine resolution. Resolution is a very important term. You're going to hear it a lot in whether HPLC or GC. And again, resolution is the separation of two peaks. Now, how do you quantitate resolution? So there are, one way to determine resolution is by looking at the difference in time, retention time, of peak 1 and peak 2. So the difference is delta T. So 2 delta T over the width, the summation of the width, will give you resolution. So when the width is large, obviously W1 plus W2, when the width of the peak is large, like in this example, of course, resolution will be poor. This is in the denominator. When the difference in retention time is large, that means they're well separated, resolution is better. So basically, this is illustrating the importance of time separation as well as the width of the peak. The sharper the peak, the more you're going to get resolution, more chance of resolution. The less it's going to spread down your column, the better you're going to separate compounds with similar interactions in your column. Okay. The other concept is, we're going to talk about and spend some time on, is resolution is a factor or a function of efficiency of the column, factor A, which has to do with number of theoretical plates. You must have heard about theoretical plates somewhere else in life. And B, selectivity, how selective your column is to the different compounds that you're trying to separate. And capacity, C, which has to do with the number of functional groups you have on the stationary phase. And with time, these functional groups can be broken off or washed off, so you lose capacity with time. That's why you can never use the column, or you cannot use the column for eternity. It has a life. You lose efficiency, selectivity, and capacity over time. So resolution is defined by these three terms. Oh, not yet. Okay. Important concept, which is number of theoretical plates. So number of theoretical plates, have you heard about that? Do you remember anything about it? Even though it's not the question, it's an answer, you will get a chocolate. Okay.
So number of theoretical plates is when you're going up column chromatography is the number of times your, I guess whatever you're distilling becomes gaseous and then condenses again and then goes back and it goes through the cycle.
Cycle, equilibration, number of equilibration. Whatever you said, it means number of equilibration. There you go. So if you remember when I showed you that video of the partition, you know, those tubes, and your liquid is moving from one tube to the other, that the extraction, partition extraction with the Grech apparatus, if you remember this, That's every tube you have an equilibrium that happens between the mobile phase and the stationary phase. Your solute, you reach a partition coefficient which is constant. Okay? Every tube, this happens in every tube. So every tube in that apparatus is a theoretical plate. So if we take that apparatus and convert it to a column, there are imaginarily divided sections in the column where there are continuous equilibrations happening. So your column could be divided, as in this, two different compartments, but imaginary compartments, where in each one there is different equilibrium happening. Not different, but equilibrium. As the solute moves down until it leaves, you have these equilibrium taking places. So this is a theoretical plate. This is a theoretical plate, TP, a theoretical plate. Number of theoretical plates is how many equilibriums happen within that column is the number of theoretical plates. Okay. At the beginning, when the column is new, you have the highest efficiency of the column. Let's say you ran caffeine on a column, and you get a set number of theoretical plate that you can calculate following the equation that has, this is the equation that you can calculate, retention time over the half the width times 5.5 and this one to the squared. So this is the equation. You can actually calculate your number of theoretical plate at the beginning of your purchase of the column. You run caffeine, you calculate N for caffeine. And N is different for every compound because every compound will reach equilibrium differently because it will interact with the column differently. Then after 6 months, you ran caffeine again, and then you find that your N went down because you're losing capacity of the column, you're stripping off some functional groups, you're blocking some functional groups, so you really lose efficiency of the column over time, and then equilibrium takes longer time to be reached. So your number of theoretical plates decreases. So when the number of theoretical plate decreases, that means your efficiency of the column decreases, and this leads to wide peaks because you have more diffusion within the particles of the column rather than having a nice sharp peak here. The broader your compound, if you have multiple compounds, then they are co-eluting because they're broad, versus here they are separating and remains sharp. Okay, I'm going to go ahead.
For the quiz, do we need to memorize each one of these equations for each?
Memorize each one of these equations. You need to know the height equivalent of a theoretical plate, but no, you don't need to memorize. You don't need to memorize this. You just have to understand that it has a relationship between retention time and the width of the peak. But here I'll talk about it more on Monday because Gary's going to talk about GC this Friday. I'm going to talk about the height equivalent of a theoretical plate because what's important is not the length of the column. What's important is the height of each plate. So height equivalent of theoretical plate is the length of the column by the N. So the length of the column by number of theoretical plate, you got the height equivalent of theoretical plate. The larger the N, the narrower are these plates. That means you have shorter height, which is good for resolution. As the height becomes bigger, like here, then you lose resolution. So this needs to remain narrow. So I will talk more about what A, B, and C stand for and what do they mean in terms of resolution. We'll start that on Monday. What I urge you, start studying in the weekend because the quiz is on Wednesday. So you really need to get going with studying and be ready on Monday to continue where we left off. Please. I still have more chocolate. I'll bring it on Monday.
So everything from nutrition labels, data, sampling, everything else chromatography, plus the stuff on Friday and Monday are all fair game.
Are all fair game. And since this year, hold on a second, this year I have 3 quizzes instead of 4 quizzes. So you might want to review quiz 1 and quiz 2 from last year to see if there's any overlap in the material. One good thing that you might like is on Wednesday, I'm not here, I'll be in Canada, so the quiz is on Wednesday. So you'll take the quiz and then leave. So you can take your time with your quiz. It shouldn't take more than 20 minutes, but you can take your time. Here you go, Zach. Almost.